Okay, good morning. Today's lecture is about quantum computation. This is an area I really like these days, so I'm trying to learn more about it myself. I guess this is a genuine picture of like a quantum computer of sorts. I'll say a bit more about it later. I have to start this lecture with a warning, which is that I personally don't know anything about physics. So if you have questions about the physical meaning of some things, you can ask them. I probably won't know. I'll try to guess. But I really don't know anything about physics, for real. But good thing is you don't really need to know anything about physics in order to know about quantum computation. I mean, you can just not know any physics and still happily study quantum computation. And that's what we're going to do. OK, so quantum mechanics is kind of a crazy topic. There's a lot of weird and strange aspects of it if you've read a little bit about it before. Let me tell you a little bit about this scientific theory I want to mention at the beginning of the lecture. Hasn't been around that long, since about the late 60s. So it's too new for your parents to have learned about it in school, for example. Well, depending on how old you are, maybe. It's a bit hard to do direct experiments to get evidence confirming this theory I'm talking about. And a few years ago, I was on Reddit, and there's this Ask Reddit thread entitled, "What scientific fact do you think will eventually be proven false?" And this is the #1 answer. And the top commenter, who was a scientist in the field, said, a lot of the theories behind it seem a little tenuous to me. And this theory I'm talking about actually is not quantum mechanics. It's plate tectonics. The theory that the continents slide around on plates and stuff. Yeah, so that might be a questionable theory, or at least one that hasn't been around that long. But what I'm not talking about is quantum mechanics. Okay, quantum mechanics, on the other hand, as a scientific theory, has been around for 90 plus years. It's been confirmed by zillions of experiments. It's not only we know that theoretically particles act in this quantum way. We actually correct for this fact when we're building hard drives and GPS devices and other things. So I'm told. So it's the most standard, 100% well-accepted theory of physics, which is definitely true. Again, so I'm told. So even though it's going to be weird, you're going to if you haven't seen it before, you're going to rebel against it a little bit. Sorry, but it's definitely true. So actually, it's going to turn out to be a good thing. It's going to challenge our intuitions about physics and the physical world, and actually give us a means to build potentially more powerful computers. OK. Well, quantum is a bit tricky, though. So in order to warm up to it, we're going to actually spend the first half of the lecture talking entirely about non-quantum stuff. Should be easier. OK? But all this stuff we'll talk about in the first half is kind of like a warm-up for quantum computation. And I'll take you on a little historical tour of some developments in computer science and related topics in the 20th century. So let's go back to all the way to the beginning, late 1930s. There were electrical engineers and telephone engineers and things. They invented the idea of Boolean circuits, which is also something we studied in lecture 2. Usually the credit goes to this guy, Shannon, who is an American, who is actually a super awesome mathematician and computer scientist. A lot of people are also working on it in the Soviet Union and Japan at the time. So they also credit these two people, Nakashima and this guy, who a picture of him cannot be found on the internet, Shestakov. Right, and they had the idea that you could build computers out of little circuits and gates, and you could analyze them with Boolean logic, which is exactly what we did in lecture 2. So let me remind you a little bit, and sorry, I'm a little sick today. As one small thing that we'll have to get used to is that in quantum computation, they always draw their circuits going from left to right, which is a little bit weird, but let's start doing that now so we're not worried about it later. So here's a little circuit with NOT, AND, and OR gates. This is the output. These are the inputs. So if the inputs are x and y, if you think about it for a second, this circuit computes the XOR of x and y. OK, so that's a little circuit. Now, there's something a little bit weird about this circuit, which normally it's fine when we're talking about circuits, but we're going to change our assumptions a little bit here. Usually in the circuits, as we normally talk about, it's OK to just have a wire carrying a bit, just split it into multiple wires. But we're going to not like that. We're going to like say that if you want to take a bit and like make two wires carrying the same bit, you have to explicitly insert a gate, which I'll call a duplicate gate or dupe gate. OK, so it just takes in one bit and outputs two copies of that bit. OK, and then just in this way, like, wires are not allowed to split in our little model here. OK. Now, it's a simple fact that actually we proved, again, back in lecture 2, that if you have any kind of Boolean function, any kind of input-output behavior that you care about, some map from n-bit strings to m-bit strings, you can always compute it with some circuit. And we know that you can compute it with a circuit that just has not, and OR gates. You can even make like a DNF formula for it. And if you take our convention that you're not allowed to split wires, then you also need these dupe gates. In fact, as we saw, or maybe as you already know, if you want to get a little clever about it, you can get down to like a smaller set of gates that still allow you to compute everything. For example, you can get rid of OR gates without even much loss in efficiency. Oh, I also want to mention this fact, sorry. This is another fact we saw, which is that every function computable by a time t algorithm can also be computed by a circuit with polynomial and t gates. So there's some kind of relationship between circuit size and like running time. And it turns out when we get to quantum computation, it's a lot simpler to talk about quantum circuits than it is to talk about quantum Turing machines. So because of this, everything today, all the computation is going to be done by circuits rather than Turing machines. That will make things simpler. OK, so back to what I was saying, which is that if you want, you can get rid of some of these gates. For example, you don't need OR gates because you can convert an OR of x and y using like De Morgan's laws to like not x, the not of the and of not x and not y. OK, so if you don't mind maybe tripling the size of your circuit, then you can get rid of OR gates. You also may well know that you can combine like and not functionality into one single gate, the NAND gate. NAND of x and y is just the not of the and. Now, to do this, at least for one way of doing this, you actually need to introduce another concept, which I want to talk about, which is scratch input bits. So what's the idea here? Well, let me show you how you can get a NOT gate out of a NAND gate. And if you can get the NOT gate, then you can certainly get the AND, right? If you have NOT and NAND, you can put them together and get AND. So how can we get a NOT gate, just given this NAND gate? Well, if you have x and you want to NOT it, you can just do the NAND of x and 1. OK, and this is what I mean by a scratch bit. So we're going to use this concept. A scratch bit is like an extra wire that you have coming into your circuit that's like always fixed to a constant, like 1 or 0. And it's not really part of the input, but you just put it in there to like help you do your computation. OK, so it's OK to have these extra scratch bits come in to help you like get knots out of, knots out of NAND gates. Now, actually, if you don't want to have this, there's a way you can still get knots out of these gates without any scratch bits. Can somebody see how to do it? Yeah? Yeah, you put x in twice. So if you do x and duplicate it, you get x and x. And then if you think about it, the NAND of x and x is the same as the NOT of x. So you can do this too, but I wanted to tell you about this scratch bit thing, so I showed you how to do it this way. OK. As long as we're warming up with stuff that like you've seen before, and maybe it's a little bit slow, I'm going to introduce you to some quantum weirdness now. In the quantum land, when they write down a bit 0, 1, they like to enclose it in these funny brackets that has like one angle bracket and one vertical bracket. So we're going to do that too. OK, but it's still in the world of basic Boolean circuits, so you shouldn't be too nervous yet. OK, so from now on, like when I write a bit 0 or 1, I'm going to put in these weirdo brackets. OK, so that was the 30s. Let's flash forward 30 more years to the 60s to talk about a topic called reversible computation, which if you have a long memory, you'll remember from homework number 1. And it was thought about by this physicist Landauer and this guy who's kind of a computer scientist / physicist, Bennett. So this is all a topic that you've seen before too in homework 1, but I'll remind you about it. So let's talk for a second about the concept of bits. So we draw these circuit diagrams, we analyze these Boolean functions and so forth. And in this world, bit is just like a theoretical concept, right? It's like 0 or 1. It's just like two symbols. But in the end, you actually physically build these circuits out of whatever, wire or something. And so in theory, there's 0 and 1, but they have like some physical manifestation when you actually build them, right? Like I'm told that perhaps in a circuit or something, you represent 0 with a low voltage and 1 with a high voltage or something. Or if you're like maybe more sophisticated and you get into like some nanotechnology, like maybe you represent your bits with a photon, and I'm told that a photon can either be horizontally polarized or vertically polarized. And some like 3D glasses work on this principle. But anyway, you have some kind of physical object that implements your bit. It kind of has two states. And what is a gate? A gate is also some physical, like localized gadget that like manipulates a couple of these physical bits. Now, in the 60s, they were actually trying to build computers and circuits and stuff in a practical way, and physicists were thinking about this. These Landauer, for example. And they were trying to think about the physical constraints and energy situation that were involved in physical circuits. And they made the following observation. Take a look at this AND gate. Let's say I tell you that the output of the AND gate is 0. Can you tell me what the input is? No, not for sure, right? Like it could be 1, 0, it could be 0, 1, it could be 0, 0. OK, it can't be 1, 1, but that's it. So you don't know. And we say that this AND gate is not reversible. Like, I can't like tell you what the input is given the output. And apparently, according to physics, like this means that no matter how you physically implement an AND gate, it must dissipate energy. Because of physics, I guess. I think it has something to do with the second law of thermodynamics or something. But somehow you put this energy in, but like some information gets destroyed. And like therefore, any physical realization of this AND gate has to dissipate energy, probably in the form of heat. Or so I'm told. So that's a little bit too bad, because if you want to use a NOT gate in your circuit, like I guess you're going to have to put energy in, and it's going to get wasted as heat. Or something like that. On the other hand, apparently, according to physics, if a gate is reversible, which I'll define shortly, then at least in principle, it need not dissipate any energy. So the physicists were like, hey, this is kind of cool. Like maybe we can build our circuits out of reversible gates, and they'll be very energy efficient. So let's think about this a little bit more, and we'll take a look at some other gates that we know and love. Here's a NOT gate, and it's reversible, right? Because if I tell you the output, that uniquely determines the input. So that's good. How about the XOR? What do you think? Or do you remember? Yeah, it's not reversible because, I don't know, if the output is 0, it could have different possible inputs. 0, 0, or 1, 1. OK, here's a crazy gate called C0. That's a little joke for you. That's its real name. It's spelled like this, though. Yeah, the first year we had like, the C0, the other C0, right? Like I didn't know about it, so then I put up this gate, and everybody laughed, and I was like, what's so funny? But now I know. Anyway, this is a funny gate. It has the following definition. It actually has 2 inputs and 2 outputs. And it's a little weird. It just passes the first input through. And the second output is you take the NOT of y when x is 1. And if x is 0, you don't take the NOT of y. So that's why it's called controlled NOT. It's like if x, then do not y down here. Otherwise, just do y. And this guy is reversible. Because, if I tell you x and x XORed with y, well, you know x. And then you can use x. If you XOR these things together, you'll get y. So you can deduce the inputs from the outputs. There's a bijection between inputs and outputs. And let me actually now try to properly define reversible by looking at this example. See, the dupe gate we saw before takes as input x, and it outputs x and x. It actually has the property that if I tell you the output, you uniquely know the input. But it's the right thing to do is say this is not reversible. We want to say that a gate is only reversible if it has the same number of inputs and outputs. This is a definition, if you recall, from like homework 1, number 4. I guess reversible is really like saying there's a bijection between the strings that are in the range of the circuit and the inputs. OK, so some of our favorite gates are reversible. Some are not. And a question, which I guess you know the answer to, if you have a long memory, is whether every function can be computed using only reversible gates. Now, of course, if you think about it, reversible gates have to have the same number of inputs and outputs, and therefore you can really only compute a function reversibly if it has the same number of inputs and outputs. And sometimes in life, we have a function that has a different number of inputs and outputs. But you see, you can still do it if you allowed these scratch bits and also garbage bits. OK, so scratch bits we talked about before. These are like extra bits that aren't really part of the input. Maybe you fix them to like ones or something. And garbage outputs are sort of the reverse. They're things that you compute that you don't actually care about, but you can just throw them away at the end. I'll give you some examples in a second. OK, and since if you want it to be reversible, the number of output bits and input bits should be the same. So there are, in some sense, n plus s input bits and m plus g output bits. Let me give you an example. Here's one more interesting reversible gate. It's called the CC not gate. It was invented by this Italian guy, Toffoli, so sometimes also called Toffoli gate. It's like controlled not. So it has 3 inputs and 3 outputs. The first input, 2 inputs just pass through. And the third output, you negate z if x and y are both 1. If they're both 1, then you negate z. Otherwise, you just leave z. It's not hard to check that this is also reversible. If I tell you x, y, and this thing, you can figure out what z was, because you know whether or not you negated here. And this is the key gate that you need, or one key gate that you need to show this theorem that every function can be computed by reversible gates. In fact, every function can be computed just using this one single reversible CC not gate. So you may or may not have found this gate on your homework. So let's see why that's the case. This is going to be like the magic reversible gate that will let us do everything. In particular, to show that we can compute every function, we just need to show that you can sort of build NAND gates and dupe gates out of this CC not gate. So let's say I do one of these CC not gates, and I put in x, y, and 1. What do I get out? Yeah, I get out x, y. And then if both of these are 1, then I flip this to a 0. Otherwise, it's a 1. So yeah, I get out x, y, and NAND. So if I want to simulate a NAND gate, I can do it with this thing. This is an example of a scratch bit. It's like an extra bit I fixed to 1 in order to help out the computation. And actually, these two things are examples of garbage bits. I have x and y as the input. I really only wanted NAND of x, y as the output. This reversible computation also outputs x and y. Well, I just say, whatever. I don't need them. I mean, I can use them if I want, but if I don't, then I can just consider them garbage. OK. Now here's another idea. What if I take this CC not gate, I put in 1, x, and 0. What are the 3 bits I get out? Yeah, that's right. I get out 1, and I get out x. And then I get out 1 if x is 1, because I negate this 0. And if x is 0, I don't negate it, so I get out 0. So I get out 1, x, and x. And that's the dupe functionality, right? This is dupe of x. And here I had 2 scratch bits, 1 and 0, and 1 garbage bit. It spat out a 1, which I didn't need. And that's it, right? Now that I have dupe and I have NAND, I can put these things together. And I'll get like maybe more and more scratch bits and more garbage bits. But I can build up any circuit I want. There's one more trick. I mean, if you prefer to be like neat and tidy, you see here one of the scratch bits was 1, one of the scratch bits is 0. It's a little convenient if you just say, I'm going to just say all my scratch bits are 1. But then how do you get a 0? Well, you can just check. If you put 1, 1, 1 into this, you get out 1, 1, and 0. So in this way, you can assume all the scratch bits are 0, because you can produce some you can assume all the scratch bits are 1, because you can produce some more extra zeros if you want. OK, so actually, this is the solution to like Landauer and Bennett's question. Actually, every function can be computed by some kind of circuit only using reversible gates. In fact, you only need these 3 input, 3 output CC not gates. And such a circuit might look like this. So usually you're computing functions that map n bits to 1 bit. It can in general map to m bits, but I drew the picture with 1 bit. So what does it look like? You have n bits that are the real input bits. You have some more scratch bits, which are just always fixed to 1. And then you have a bunch of these CC0 gates that just act on 3 of the bits. And somehow this is how you would draw this diagram. This one means that like you negate x1 if x2 and this last one are 1. Otherwise you don't, and these ones get passed through. And at the end you get like a bunch of garbage bits which you don't care about, and maybe your output bits. Or maybe you have multiple output bits here that you care about. And these start to actually look not as familiar in terms of circuits. It's a weird situation because every gate has the same number of input and output bits. It's really like every wire just kind of goes like straight through. Or like if you were physically realizing this, you'd have like some object associated to each of the input bits and scratch bits, maybe like I don't know, with a wire with some voltage on it. And then kind of you just do gates to like different wires. But somehow like the wires maintain their identity throughout the whole computation. Another like mildly, I don't know if it's a sad story, but a fact of life is, Bennett, for example, thought about this great idea and like showed that you can compute any function with these, in a purely reversible way, and therefore in principle it need not dissipate any energy. It seemed like it ended up like not mattering practically. Like that wasn't like the big problem in making computers, this energy dissipation. It turned out to not really matter if it like dissipated energy or not. I mean, okay, I guess your laptop gets a little bit hot, maybe. It's for a different reason, I'm not really sure. So for a while, this whole reversible computation thing was more like a kind of curiosity of history of physics and computer science. But as we'll see, it kind of made a comeback a little bit later. OK, the last thing I wanted to say on this little topic of reversible computation, one time I gave a lecture about that included this fact that every function can be computed by a reversible circuit. And somebody asked a question, which at first I thought, like in my head, like, oh, it's kind of a dumb question. But then the more I thought about it, the more I realized it was like actually a genius question. Like it was a really great question. And I will ask it now to you in the form of a puzzle. Let's consider the multiplication function, which takes 2 n-bit strings and outputs their product. Okay, it takes 2 n-bit numbers written in binary and outputs their product. That's a simple enough function. We know you can do it in polynomial time. You can do it in n-squared time. You can even do it in close to linear time. So we know there's some polynomially many, a gate with polynomially many circuits that implements multiplication. It's not too hard to like explicitly write it down. And now we know from the previous theorem that it has a circuit that uses only reversible gates. So it takes in 2 input numbers, outputs their product, and like the whole gate is reversible. So the question is, why don't we just like literally take the picture, like whoop, turn it around, reverse it, and now we get a circuit of the same size that does factoring. You put in like a number and it spits out the, the 2 factors. That would be awesome, right? I mean, then we would have like an efficient circuit for factoring. So what's the problem here? Yeah?
The range does not include every possible number.
The range does not include every possible number. Yeah, that's true. So like what happens when you put in like a number? I mean, it's related to the answer. Yeah, do you have a? Yeah, I mean, these are related. This is basically the answer. Like, remember when you compute a function, like you have these extra scratch bits and also these extra garbage bits. And like, if you go to this picture, like imagine this was multiplication. These were the real inputs. OK, multiplication has more than 1 output bit. So it has some actual output bits that gave you the product. But it also has some garbage bits. So you could put the number you're wanting to factor into the, let's say I even told you it had exactly 2 factors. You could put it into the output and try to run this backwards. But you would need to like guess the correct garbage bits that you would get if you did the multiplication forwards. Yep.
But I mean, it seems like if we're taking 2 in-bit numbers, so we're assuming that there's no scratch bits, right? Each input takes up the full
No, I mean in general, when you do this reversible, when you take a circuit made with like and or not gates and you turn it into a reversible gate, you definitely need scratch bits.
Oh, I see. Okay.
So yeah, so you'll always have a number of scratch bits which is maybe linear in the size of the circuit. So yeah, there's actually going to be, you kind of like have to like guess the garbage bits which would cause the circuit to make output all ones in the scratch bit positions. And that's kind of like the SAT problem. Yeah?
Is it possible to set it up so you end up with all ones in the garbage output bit?
It is. Yeah, it is. Oh, all in the garbage output bits?
Yeah. Or like all zeros?
No, not in general. You can't really ensure that. In some sense, you don't really know what you get in the garbage bits. Okay, well, that's a little puzzle that I thought was interesting. But let's move on in our story from reversible computation. Okay, now the next development that's sort of in the story towards quantum computation is probabilistic computation, which is also something that we've studied, and it was invented by a lot of people in the 70s. Maybe these are 4 of the big names in the field of probabilistic computation theory. Okay, and quantum circuits, as we're going to eventually define them, are extremely, extremely similar to probabilistic circuits. So we're going to spend some time talking just about probabilistic circuits. Okay, so it's just like adding coin flips in a way to circuit computations. So let's say I have a little circuit with one gate, a NOT gate, and that's a coin. I flip this coin to get either 0 or 1, and I pass it through the gate. Well, let's represent this mathematically a lot like we did in the random walks lecture, where we have a row vector representing the state of this bit, which is 0 with probability 50% and 1 with probability 50%. Okay, so I have row vectors. Their coordinates are going to be indexed by like the different states that the bit can be in. Well, when I pass it through this NOT gate, you know, it flips it, but the resulting output bit is again 50% 0 and 50% 1. Okay, so far so easy. Let me take this C NOT gate and do a similar thing. So remember, it passes x through on the top, and it does x XOR y on the bottom. And imagine this is what I'm going to do in this little circuit with one gate. I'm going to flip a coin for the top bit, and I'm always going to plug in 0 to the bottom bit. Okay? So you should think about what's going to happen out here while I'm talking. Okay, so again, we can represent this bit state as it's 50% 0 and 50% 1. And as long as we're doing that, we can also represent, so you see when you pass it through the output, this one's definitely going to be 50% of the time 0 and 50% of the time 1. And if you think about it for a second, if I ask you what's the probability distribution on this output bit, it's also half the time 0 and half the time 1. And if I just said, like, there it is, I've analyzed the circuit, this is correct. Each of these bits is equally likely to be 0 or 1. But to just put it like this is extremely misleading. So why is that misleading? Yeah?
These are independent things.
Yeah, they're not independent. That's right. In fact, what property do they have? Yeah?
Not if one is the other.
Not quite. They're actually always equal, I think. And that's like not captured. I mean, if you have, they're both random bits, but they're also always equal, right? If you put in 1, you get 1, 1. If you put in 0, you get 0, 0. So this doesn't really capture like the correlations between them. So the better way to analyze this circuit, or like the right thing to say is, these two wires have like a joint state. Hope you can read this. They can either be 0, 0, 0, 1, 1, 0, or 1, 1. And it's like 50% of the time they're 0, 0, and 50% of the time they're 1, 1, and 0 of the time they're 0, 1, or 1, 0. Okay, so to actually kind of capture exactly what's going on here, you want a row vector, a probability vector that has one coordinate for each of the 4 possibilities. And it tells you all the probabilities of seeing those 4 outcomes. Okay. In fact, as long as we're doing that, we may as well also imagine that we did that for the input bits. There are two input bits. One was deterministic. It was always 0. The other was randomized. But you can still say the two input bits, there are 50% chance of being 0, 0, 50% chance of being 1, 0, and 0 chance for the other two possibilities. And so this is almost like what we have here is basically like a little, like one step in a Markov chain or a random walk. You see, this thing is the transition matrix for this C NOT gate. Okay, it really says that like if this row, for example, says if the output bit, or sorry, if the input bits are 0, 0, the output is 0, 0. The input bits are 0, 1. You have a 1 here because the output bits are 0, 1, and so forth. The rows tell you like how the input bits transition to the output bits. And just like in the random walks lecture, I mean, you can get these probabilities given any probability distribution over here by just doing this vector matrix multiplication. You know, you could have any distribution on input bits here, and like if you do this multiplication, this vector times this matrix, you know, 50% of the time you're 0, 0, in which case you kind of do this row and you get to 0, 0 with probability 50%, and so forth. Any questions about that? This is where it's going to start to get a little, you know, interesting. Okay. You have a similar situation for any other gates. For example, this CC NOT gate, it has 3 inputs and 3 outputs, so it has an 8 by 8 transition matrix. You know, just for each of the 8 possible incoming states, you know, this matrix has a 1 in the column corresponding to the outgoing states. Okay, and these are deterministic gates, so they always just have 1, 1 in each row. Now, I told you I'm going to talk about randomized computation. And once we have this kind of Markov chain or random walks type setup, we can also use it to analyze probabilistic gates. So I invented now this blue probabilistic gate. It's not very interesting, but I invented it just for the purposes of illustrating the math. So it's a little gate that it's not deterministic. It has 1 input bit and it has 1 output bit. And it's kind of like a NOT gate, but it's got some noise in it. Okay, so if the incoming bit is 0, you output 1 with probability 0.8. So 80% of the time you implement NOT. And if the incoming bit is 1, then you output 1 with probability 10%. So 90% of the time you do the NOT. Okay, so there's no special meaning to it. Maybe you actually built some physical device to try to implement NOT and like, I don't know, it was a bit flaky, so it did this. But it's going to be nice for illustrative purposes. So it also has a transition matrix, kind of corresponding to like the transition matrices in random walks. And it looks like this. It doesn't have a single 1 in each row because it's probabilistic. So this is like saying if the incoming bit is 0, your outgoing bit is 0 with probability 0.2 and 1 with probability 0.8. And similarly, if the incoming bit is 1, the probabilities are 0.9 and 0.1. Okay, so it's a 1 input, 1 output gate, so it's a 2 by 2 matrix. In general, if you had a gate that had k inputs and k outputs, then you would get a 2 to the k by 2 to the k matrix. And it would actually be what's called a stochastic matrix or a probabilistic transition matrix. It's just one where all the rows are non-negative numbers summing up to 1. Right? For each incoming possibility, you have like a probability distribution on the outgoing possibilities. Another way to say it is it's a matrix which preserves probability vectors. Whenever you multiply it on the left by a probability distribution vector, you get out some other probability distribution vector. So this would be an example of some like weirdo 2 input, 2 output probabilistic gate. You know, for each incoming possibility, like if the input bits are 0 and 1, it outputs 0, 1 with probability 0.6, 1, 0 with probability 0.4, and never for 0, 0 or 1, 1. Any question about this? Okay. So let me do an example of how you can reason about probabilistic gates using these matrices. It's kind of the trickiest part of the lecture, but it's good that it's now because there's still no quantum yet in this lecture. This is probabilistic circuits. And you would figure this out yourself, no trouble, if I asked you to. But I'll show it to you now. So here's a little circuit I drew, a probabilistic circuit with 2 input bits and ultimately 2 output bits. First it does a C naught, and then it does this weird noisy naught on the second bit, and the last thing it does is this weird noisy naught on the first bit. Okay, and I just want to show you how can you analyze the behavior of this circuit. Or if I tell you like what bits are coming in, what is the probability distribution on the bits coming out at the end? That's the kind of thing we're going to care about. And there's nothing especially tricky about this, but we're going to do with these vectors and matrices in like the random walks kind of fashion. And let's even do an example where we start with this same case. I'm always going to put in a 0 for the second bit, and I'm going to flip a coin 50-50 for the first bit. And now I'm going to ask, what is the distribution of the 2 output wires when you pass it all the way through this case? Okay, if you don't want to listen, you can try to do it yourself on a piece of paper and compare notes with me when I get to the end of a few slides. Okay, so we're going to kind of imagine going left to right, and sort of at each time before we go into a gate, we're going to think about what is the probability distribution on the 2 bits so far. So at the beginning, we saw this before. There's a 50% chance of having 0, 0, and a 50% chance of having 1, 0, which we represent by this line. And now we put it in the transition matrix, the matrix for the C naught gate, which is actually a deterministic gate. So each row just has 1, 1 in it. We multiply, and we get the probability distribution on the 2 wires at this time. Okay, and this we saw already. We did this before a few slides ago. At this point, there's a 50% chance that they're both the same, 0, 0, 50% chance that they're both 1s. Okay, so here we are now. And now we're going to go through the next gate, which does this weird blue gate on the second bit, which is kind of like a negation, but there's some noise. So actually, let's think for a second what's roughly going to happen. You've got either 0, 0 coming in or 1, 1 coming in. And you're roughly probabilistically going to negate the second bit. So when we come out here, it's mostly going to be either 0, 1 or 1, 0. Okay, so they're probably going to be different coming out. But let's just check exactly what happens. Now, the first instinct you might have is you'd say, OK, let me write down the transition matrix for this gate and multiply them. But there's like a type mismatch here, okay? Something looks like it's going wrong, because you cannot multiply a length for a vector by a 2 by 2 matrix. And the reason is this matrix is just a transition matrix for 1 bit, and it is true that we're just applying it to 1 bit. But overall, we have to care about the distribution of both bits together. So this is maybe the only slightly non-obvious step. You need to expand this transition matrix for the 1-bit gates so that it acts on 2 bits together. And let me just show you what that is. This expansion takes this matrix and turns it into a 4 by 4 matrix. And in just the natural way, right? This 4 by 4 matrix is saying, okay, if 0, 0 is coming in, we always just leave the top bit alone. So you're never going to get a 1 in the first bit of the output. And assuming you have a 0 in the first bit of the output, it's just like up here. I mean, you output 0 for the second bit with probability 0.2, and 1 for the second bit with probability 0.8. Okay, and you're going to get a copy of this matrix down here, and 0's here. And when the incoming bits start with a 1, the outgoing bits are always going to start with a 1, because this gate doesn't touch the top bit. So you kind of get a copy of the matrix down here, and 0's down here. Okay, this is the only confusing part. So, is there a question about it? Okay. So now we have the full story on like how this object transforms a pair of bits. So we can do this matrix multiplication. This is really like we're doing like 3 steps in a Markov chain, but where sort of you do a different kind of transition at each step. The C0 transition, this bit transition, this bit transition. Anyway, if you do this matrix multiplication, you get out this answer. you have a 10% chance of 0, 0, 40% chance of 0, 1, 45% chance of 1, 0, and a 5% chance of 1, 1. And this is exactly like we kind of expected, right? We kind of expected most of the time you're going to get two opposite bits. Okay, so that's the state of the two bits out here. And last step in the circuit is to do the negation on the first bit. So probably at the end we're going to get two bits that are the same, but like this noise is going to make it not exactly correct. It's kind of collecting up. So again, this is the transition matrix for this little gate. But again, we need to expand it so that it's 4 by 4. And now it looks a little bit different. Why does it look a little bit different than this one?
The first bit instead of the second one?
Yeah, it's just because this one is operated on the first bit, so kind of, you're changing the first bit instead of the second one. So I mean, if you do this gate to the first bit, when 0, 0 is coming in, you never change the second bit, so that's why you have zeros on the columns where 1 is in the second bit. Okay, so the matrix entries kind of go into a different, funny way, but it just acts like you would expect. Okay, so we can stick that matrix there. The final outcome. These are the 4 probabilities of the 2 bits being in each of the possible states. You kind of see that most of the probability kind of is on 0, 0 and 1, 1, but not all of it. So that's the final answer. And now I might ask you the following question. You see, when you do this experiment, imagine like you built the physical device implementing this, and you plug in the bits, but you didn't look at it yet. Okay, so the experiment ran, the 2 bits are in some state, but you didn't look at it yet. And now the day comes where you're going to look at it and say, I wonder like what the final outcome of the top bit was. That's called measuring. And sometimes people draw a gate for it. This is supposed to be like a detector or something. And I can ask you, what is the probability that you'll see a 0 in the top bit? What is it? It's 55%, right? Because these are the 2 cases where you see a 0 in the first bit. They add up to 55%. The probability you see a 1 in the first bit is 45%. And actually, if you wanted to keep going, like maybe you measured it and now you're going to stick this last wire into some other circuit. In some sense, the state kind of collapses. If I look at the top bit and it was 0, then I know that afterwards the state is either 0, 0 or 0, 1. If I don't look at the second bit, I'm not sure. I still have some uncertainty. And so the probability would be 0, 0. It's like a conditional probability thing. It's 0.425 over 0.55. And the probability at 0, 1 is 0.125 over 0.55. Okay, any questions about this? This is like a way you could analyze probabilistic circuits. It's sort of the only way you can analyze it. Now, before we move on to quantum, let me give you a final thought on probabilistic circuits. If I give you like a probabilistic circuit with n incoming bits and n outgoing bits, like imagine n is 100, and I even tell you like what is the distribution on the input bits, and I say, okay, compute for me the distribution on the output bits, that would be very annoying to you, right? Because you have to go through all these things, and you have to maintain a vector of probabilities of like 2 to the n. 2 to the 100 if there's like 100 input bits. And you can't really do that in practice. It's enormous. And it's very tough. So you probably couldn't write it down. But one thing you could do is just say, like, if you really cared about the output probability distributions, you could just say, well, I'll just run the circuit like a few times and like measure them and see what the probability distributions were. It's kind of too hard to literally compute them because you need to write down these exponentially like long vectors. And also, these vectors are really just modeling your uncertainty, the experimenter's uncertainty about what's going on, right? In real life, if you do this experiment, you plug in like n random bits and it goes through some kind of random circuit, it's actually always in some state, right? Like every bit is actually 0 or 1. The probabilities are just modeling your human uncertainty about what they are, right? In actuality, they're not in a random state. They're some actual bit values. Okay, so now we're halfway through the lecture. It's the time to start talking about quantum computation. Now that we're warmed up. And the cool thing is, quantum computation is exactly the same as probabilistic circuits that we've just been doing for the last 15 minutes. Totally exactly the same, with like basically one twist. And the twist is now that the state vectors can have negative entries. So it's kind of like you can have negative probabilities for things. Now, they're not really probabilities anymore, because probabilities cannot be negative. That's a fact of life. So we just changed the name, and they're called amplitudes rather than probabilities. And probabilities are supposed to have the property that if you add them all up, you get 1. And when they're amplitudes instead, it's a different rule. It's almost a nicer rule. It'll be that the squares of the entries always add up to 1. Okay, so probability vectors, like they're non-negative numbers adding up to 1. Amplitude vectors, they're possibly positive or negative entry vectors, where the squares add up to 1. Other than that, that's basically it. That's quantum computation. I mean, I'll expand on this fact, but that's the high level of the story. Okay, so moving forward from the 30s, the 60s, the 70s, move into the 80s and 90s, and to the idea of quantum computation, which is generally credited to these two people, Feynman and Deutsch, both physicists. And let's return to this question of what is a bit, and how in theory, it's just a symbol, 0 or 1. But when you physically implement things, it's like a, has a physical manifestation. Perhaps it might be a photon, which could be in this horizontal state or vertical state. Well, turns out if you crack open a physics textbook that was written any time after 1920 or something, so in the last 100 years, they'll actually tell you it's not true. According to the physical, actual laws of quantum mechanics, which indeed govern the universe, a photon state can be horizontal or vertical, but it can also be any superposition of these two of the form alpha times 0 plus beta times 1, where alpha and beta are real numbers with this property that the sum of their squares is 1. And this is kind of just like also a theoretical symbol or formalism for describing the state. It's like amplitude alpha on 0, amplitude beta on 1. And it's just a fact of life that the actual possibilities for what the state of a photon or any other these particles is like this. Yeah, so that's kind of weird. In fact, even that's not true. If you look at your quantum mechanics textbook, these amplitudes, alpha and beta, are even allowed to be complex numbers. So it's not just negative probabilities. They can even be complex probabilities or something. And so really, a photon state, it's like alpha 0 plus beta 1, where alpha and beta are complex numbers whose absolute values squared add up to 1. However, it's a fact that if you only care about quantum computation, you're not a physicist, you just want to build quantum computers, without loss of generality, you can just assume that all the amplitudes are real numbers. So that's what we're going to do. Why, there's already going to be enough craziness going on, let's just do that. So no complex numbers for us, it'll always be real numbers. Okay, but it's still kind of amazing and crazy that these amplitudes, whatever they mean, can be positive or negative. Okay, so instead of calling these objects bits now, they made this little joke, they're called qubits, so it's spelled like that. So a qubit is like a mathematical formalism for the state of a particle. It's a theoretical concept. It's like an expression, if you will, alpha 0 plus beta 1, where these amplitudes are real numbers whose squares add up to 1. And we also write it, just like the probabilistic scenario, as a vector, where the coordinates are 0 and 1, and the entries are these amplitudes. So a little qubit corresponds to a length 2 vector. Yeah?
Is the alpha basically just kind of the throwaway of what we had left from the beta? Because it doesn't actually contribute anything to the value, right? Because it's getting multiplied by S0.
Yeah. This is just symbolism. So this is just you shouldn't. In some ways, you shouldn't think of this as multiplication. It's just like a symbolism. There's a way to think about it where like these things are actually vectors, but we won't do that. You should just think of this as a symbolism, saying that the state. I could invent like symbolism for a probabilistic bit. If I wanted to say it was 30% of the time 0 and 70% of the time 1, I might have like invented some symbols where I would say, I'm just going to call that 0.3 times 0 in funny brackets plus 0.7 times 1 in funny brackets. And like that would be my symbolism. And that's what we're doing here. It's just a way to write down the state of 1 qubit. And actually, eventually we're going to more commonly write them as vectors, where the amplitudes are in a row vector. And this condition that the entries squared add up to 1, you can express this geometrically. If I give you a vector, right, what is the length of the vector? It's the square root of the sum of the squares of the entries. So to say that the square of the length is 1 is to say that the sum of the squares of the entries is 1. And you can equally just say the length is 1 because the square root of 1 is 1. But this is the condition. This vector should have length 1. It's a normal vector. Okay, so you have 1 qubit, and you think of it in this vector way. Its state is actually sort of a point on the unit circle, or a vector on the unit circle. And like, that's life. I mean, it's weird, but it is what it is. That's the laws of quantum mechanics. You should not think of it as like, alpha probability on 0 and beta probability on 1. You can't, because like alpha and beta might be negative. It's still kind of similar to a probabilistic mixture, but it is what it is. That's life. But it's actually not a sad fact of life. It's going to be like a happy, cool fact of life, as you see by the end of this lecture. Now, the idea of quantum mechanics is trying to build actual computers or circuits and sort of take advantage of the fact that these particles that are storing your bits can be in like these weird superposition states. And we prefer not just to have 1-bit circuits, but 2-bit, 3-bit, 4-bit circuits. So let's talk about what happens if you have 2 qubits. So maybe you have some photon, and it's in a state alpha, beta are its amplitudes. It's like hanging out. And then like somebody brings you another photon, which is in some other states, maybe alpha prime, beta prime. And then you just put them next to each other, and you look at them and say, that's like my new system. It's got 2 photons. Well, same with when you put 2 coin flips next to each other. They actually have a joint state. And in this story I told you, where you had some photon in state alpha beta, and somebody brought you another one in state alpha prime beta prime, when you put them together, it's called like, you just prepared them separately. And the joint state is like exactly what it would be if they were like independent probabilities. Okay, their joint state is like this. They can be 0, 0, 0, 1, 1, 0, 1, 1, and these are the amplitudes you get. That's the rule. And same as if they were probabilities. And one thing you can check is, let's say we take this vector of 4 amplitudes and you add up the squares. If you look at the arithmetic, it's like alpha squared plus beta squared times alpha prime squared plus beta prime squared, which is 1 times 1, which is 1. So it also has the property that the sum of the squares of the amplitudes is 1. And in general, no matter how many qubits you have, it's going to be represented by a vector with amplitudes that when squared add up to 1. Okay, so another way to write it formally is like, this is a formal way to write it where these are the 4 amplitudes, alpha, beta, gamma, delta, and their squares should add up to 1. And we also write it as a vector alpha, beta, gamma, delta, like this. And again, this is saying that the length of this vector, as like a normal vector, is 1. So here's an interesting example of a state that 2 particles might be in. 1 over root 2 amplitude on 0, 0, and 1 over root 2 amplitude on 1, 1. Or if you write it in vector notation, it's like this. You check that the sum of the squares here is a half plus a half, which is 1. 2 particles that are in this state are said to be called an EPR pair. It stands for Einstein, Podolsky, and Rosen. And they were very unhappy about the fact that particles could exist in this state, but sorry, they can. They got their name put on the concept at least. And what made them unhappy is that these numbers are not of this form. Okay, they're not of this form because if they were, if this is 0, then either alpha or beta prime would have to be 0. But if alpha were 0, this would be 0, which it's not. If beta prime were 0, then this would be 0, which it's not. So they're not in this like separated form, and the terminology that's used is they're entangled. Okay? And it just means that like you cannot get into the state just by like taking one photon from over here, one photon from over here that they've never seen each other before, and sticking them next to each other. But they can eventually get into this state. So in general, if you have n qubits, like n photons or something together, their state is like a vector, represented by a vector of length 2 to the n, whose length is 1. The sum of the squares of the entries is 1. And the coordinates are indexed by the n-bit strings. Okay, and this is actually where, the computer scientists have a good idea. Like the physicists were always, playing around with 2 and 3 qubits. The computer scientists were like, hey, let's go to n qubits and build something. Okay, so I talked about quantum bits. Maybe they have a physical manifestation as photons or some other kind of object. And there's also a notion of quantum gates, which are again physical objects that like act on qubits. So let's imagine what a quantum gate might look like. It's going to turn out that quantum gates always have the same number of inputs and outputs. So here's one with 2 inputs and 2 outputs, and I'm going to call the gate U. So the incoming bits have some state, given by 4 amplitudes for 0, 0, 0, 1, 1, 0, 1, 1. And the gate is again going to be represented by a 4 by 4 matrix, just like in the probability world. So it's going to be some kind of transition matrix, but it's not going to be the kind we saw before. It will be a little bit different. And the reason it's going to be a little bit different is as follows. You're going to get the output amplitudes for the 2 photons or whatever by doing the same thing you always do, a vector times matrix multiplication. But you see, the rule of quantum mechanics is that the amplitudes always have to, when squared, add up to 1. So if this U is going to actually physically exist in the world, it has to have the property that whenever you plug in 4 amplitudes whose squares add up to 1, the result is 4 numbers whose squares add up to 1. And that's a kind of constraint on the matrix U. It has to have a special property that whenever you plug in a vector whose length is 1, it spits out a vector whose length is 1. If you know enough linear algebra, this is actually why when quantum stuff was first got invented in the early 20th century, like the mathematicians were very happy because they're like, hey, that's like a linear algebra concept that we know a lot about. Like, this is great. The property that of a matrix that when you like plug in a length 1 vector, you get out a length 1 vector. It's the same as saying it's a transformation on space that doesn't change lengths. It's kind of like a rotation or a reflection or something. And there is a linear algebra terminology for that. It's called the unitary matrix. And unitary just means it's length preserving. Whenever you take a length 1 vector, multiply by U, you get out a length 1 vector. And the linear algebra people know a lot about these matrices. They're quite nice. One fact that they have is an equivalent condition, it's not too hard to prove, is that if you do U times U transpose, you get the identity matrix. Yeah?
Is it the same as a orthogonal matrix?
Great question. You know some linear algebra. If all the entries are real and you're always talking about real vectors, then this concept is called orthogonal matrix. In the case where the vectors can have complex entries, which is really like the true case, although we're not actually talking about it, the concept is called unitary matrix. But since we're only going to talk about real matrices, if you feel more comfortable or you know about orthogonal matrices, you can just pretend every time I say unitary that I'm saying orthogonal. Yeah?
So these preserve angles as well?
Yeah. Okay, so this, it's not very important for you to know this. Well, I guess you can know this fact. You don't need to know the proof, although it's not hard. This is the identity matrix, the one with 1s in the diagonal and 0s elsewhere. And this stagger here represents the transpose, where you flip rows and columns. And if you're working with complex numbers, you have to take the complex conjugate of all the numbers. Okay, but mentally you can just think about it as any linear transformation space. It's like a rotation and a reflection, kind of. That's the right picture to have in mind. Something that doesn't change lengths. And actually, if you take a look at this, if you take this equation and multiply on the, let's see, maybe you need to multiply on the left by U inverse. It's equivalent to saying that the inverse of the matrix, or the inverse of the transformation, is the same as the transpose. Never mind, the point is that this shows that this matrix U has an inverse. Okay? And mentally, I mean, this picture of U as being like either a rotation of space or a reflection of space, both of those things are reversible, right? So, I mean, it doesn't somehow lose any information. You can always go back. An inverse exists. And that actually is the reason why we talked about reversible computation, because it turns out with quantum circuits, all the gates have this reversibility property. Let me give you some examples of quantum gates. These are theoretically described gates, but they have the property that they can be physically implemented in the real world. So the NOT gates, not only is it reversible, it's unitary. It preserves vector lengths. You see, if you think of it as normally only operating on good old bits, 0 or 1, but it can still operate on probabilistic bits, and it can still operate on quantum bits too. And it has the same property, like it carries 0 to 1, and it carries 1 to 0. So if you plug in a photon with amplitudes alpha beta, you get out a photon with amplitudes beta alpha. And this is length preserving, right? If alpha squared plus beta squared is 1, then beta squared plus alpha squared is 1. And like, so it's okay. So that's a nice quantum gate. In fact, any of these reversible deterministic gates can also be quantum gates. So this C0 gate that had this transition matrix, you can still plug in like qubits to a C0 gate. And it has 2 incoming qubits. If the amplitudes are alpha, beta, gamma, delta, then you multiply it against this matrix. It just does the C0 kind of to the amplitude. So the result is alpha, beta, delta, gamma. And again, you see, like, that's all cool. Like, if these numbers, when squared, add up to 1, then this is just a rearrangement of the numbers. So they also add up to 1 when you square them. CC0 has the same property. So far I showed you 3 like normal deterministic reversible gates, and any normal deterministic reversible gates can also be a quantum gate. But let me now show you like a truly quantum gate that really, it only makes sense in the world of quantum. It's the most important quantum gate. It's called the Hadamard gate, and it's a very simple gate. It takes input 1 qubit and outputs 1 qubit. Okay, you like put a little photon in, and shoots out the photon in a different state. And here's its matrix. It's a 2x2 matrix, and you can check that it's unitary. I mean, you can check that if you do this matrix times its transpose, you get the identity matrix. Yep.
So, is there like what does it mean if one of them is negative? Does that have any like actual like meaning?
Yeah. I mean, you can even ask what does it mean when like some of the amplitudes are negative.
Right. Yeah.
And somehow there's no deeper meaning. It's just like a weird fact of life. Yeah. Sorry. So what happens with the Hadamard gate? If alpha and beta are the amplitudes coming in, you do this vector times this matrix, and you get this 2 entries. You know, 1 over root 2 alpha plus 1 over root 2 beta, and this one for the 1 amplitude. You can also check that if you square these 2 numbers and add them up, like you'll get some cancellation, and you'll get alpha when you square these numbers and add them up. So alpha squared plus beta squared is 1, and so is the sum of the squares of these guys. And somehow this like negative sign and the cancellation causes some potentially interesting quantum magic to happen. And like all of the glory and the awesomeness of quantum computation, such as it is, comes from the fact that somehow with like negative amplitudes, they can like start to cancel each other out. It's hard to say. In fact, let me just show you something that's a little bit interesting. This is a quantum gate, and now I'm going to actually imagine a little tiny quantum circuit with only 1 qubit and 2 gates, both of which are Hadamard gates. First you do Hadamard to the qubit, and then you do Hadamard again. And let me even imagine that you like definitively stick in a qubit that's in state 0. That's like alpha is 1 and beta is 0. So it's just 0. And what comes out after you do the Hadamard gate is a particle in this state, some kind of superposition of 0 and 1 with amplitudes 1 over root 2 and 1 over root 2. Hadamard gate is like a little bit like a randomized gate that flips a coin, but don't take that analogy too seriously, but it's a little bit like that. The funny thing is though, if you plug this into Hadamard gate again and like do the multiplication again, you get back to the state 0 that has 1 amplitude on 0 and no amplitude on the state 1. So that's a little bit interesting. This is kind of an example of these calculations. Like, it's not exactly true, but it's kind of like you unflipped the coin. You know, like it used to be in some weird superposition state. When you do the Hadamard gate, it went back to its initial state. Again, it's not clear if that's exactly a right mental picture, but sort of. Okay, so all these 4 gates we saw, naught, C naught, CC naught, and H, they're all quantum gates. And the point is, actually, these gates are all physically realizable in real life by, like, I don't know, you have like lasers firing at the photons or something. I'm not exactly sure. It's up to it. It's like an engineering issue. But you can actually build these gates physically. And actually, any unitary matrix can be physically built in principle. There's actually infinitely many of them. Although that's not too weird, right? Like, you can actually have infinitely many different probabilistic gates too, right? You can have like a coin flip that is true with probability 0.5 or 0.51 or 1 over pi, or I mean, there's infinitely many possibilities for that. It doesn't freak us out too much though. And similarly with quantum mechanics, there's a very nice theorem that says, sort of without loss of generality, you only need to have quantum circuits that have the CC naught gates and the Hadamard gates. Anything you can build with another collection of gates, you can equally well build with just these 2 gates. It's really quite like the theorem that you only need goop and NAND for classical circuits, or this idea that we explored on the homework, which is that if I give you Bernoulli a half, you can pretty much get Bernoulli P for any real value P. So this is a theorem I like a lot. It's proved by this guy Yaoyun Shu, and I like it because it means you can forget a lot about like all this complex numbers and like unitary gates and everything. You can just say like, okay, quantum circuits are allowed to have CC naught gates and Hadamard gates. That's it. Go nuts. It's actually a little bit convenient to also allow C naught gates. I mean, you can build a C naught gate out of these 2 gates, but it's convenient for doing little examples to also allow C naught gates. Okay. So let me give you an example of a slightly more complicated quantum circuit. It's going to have 2 qubits. And it's going to do Hadamard to the first one and then CC naught to the 2 of them together. And let me imagine even that I definitively plug in 0 and 0 as my 2 qubits. So the amplitudes are like 1, 0 and 1, 0. Now, if I did this super formally, I would even already consider these to be a joint state. But the first thing we're going to do is to just apply H to one of them. So we can imagine, we did that over in a different building. We applied H to the 0, and then somebody brought in the second photon, 0, and then they got together before they entered this gate. So let's just imagine we do H directly to 0. So this is the H matrix. And as we saw, just a couple slides ago, when you apply to 0, you get 1 over root 2 amplitude on 0 and 1 over root 2 amplitude on 1. Okay, and here we have 1 amplitude on 0 and 0 amplitude on 1. And we're going to just put them next to each other because they're about to go into a gate together. So we saw before the rule there. We need to write them as a joint state, and we just take the sort of the product of the amplitudes, like as if they were probabilities that were independent. Okay, it's the same rule. So going in, before the amplitudes were 1 over root 2, 1 over root 2, and down here they were 1, 0. So together, going in, it's like 1 over root 2 on 0, 0, 1 over root 2 on 1, 0, and the second qubit is never 1. Okay, so then we got our 2 qubits into this state. And then here's the matrix for CC naught. We just multiply and we get 2 particles in this state. These are the amplitudes. And actually, I mean, the other symbolism for writing this is like this: 1 over root 2 amplitude on 0, 0, 1 over root 2 amplitude on 1, 1. And that's that EPR pair, this entangled EPR pair that I talked about earlier. Okay, and so those are entangled qubits now. Once they kind of went into a gate and like kind of changed their state together. So yeah, this is the amplitude situation on these 2 bits. Now imagine I now decide to look at them. So I built like a little physical device with the lasers and whatnot. I fired a couple photons into it. They came out. But I haven't looked at them yet. But now, like in probabilistic circuits, I'm now going to like look at them, and that's called measuring them. And it's a fact of life that when you actually like look at a photon with like a photon detector, it's actually always only horizontal or vertical. So you never observe it in like a kind of superposition of states. It's always in some state when you look at it. That's another like odd fact of quantum mechanics. But there's a rule about what you see when you finally observe it. And it's a rule you might guess, given that amplitude squares always add up to 1. The rule is, if you have 2 photons in like this state, and then you look at them, it kind of goes into the state 0, 0 with probability 1 over root 2 squared, and goes into the state 1, 1 with probability 1 over root 2 squared. Just half-half. So when you actually do that, half the time you'll see 0, 0 on the qubits, or horizontal, horizontal. Half the time you'll see vertical, vertical. So this is a phenomenon where you like observe some particles and it like, I don't want to say it changes their state, but it kind of like fixes their states. Yeah?
So maybe you just haven't gotten there yet, but it's not clear to me what's gained from
all of this stuff?
Yeah.
Yes, it's not clear at this point.
Okay.
I'll say a little bit later.
Okay.
Yeah, it's like, there's actually a bit of a dilemma here, which is like, for me in this lecture, I had like a couple choices. Like I could tell you like some stories about quantum computers and what you can do with them, but like then there wouldn't be enough time to like actually see like really the details of how quantum computation works. Or I could show you this, like how quantum computation really works, and then there's like barely any time to do any examples. It's like, so I had to choose one or the other, so of course I chose to show you the math. You know, it's like I'm trying to like teach you all the syntax in a new programming language and prove like, you know, build like a cool project in that language, like all in one lecture. There's no time for that, so I start at the beginning even though there's not going to be a cool ending. Yeah. Okay. We're almost done the rules at least. So with quantum measurements, here's the rule. If you have a particle whose amplitudes are alpha and beta and you measure it, then you observe 0 with probability alpha squared and 1 with probability beta squared. And these numbers are positive numbers, not negative numbers that add up to 1. So this like makes perfect sense. And furthermore, somehow the state collapses, just like with probabilities, probabilistic bits. You know, once you measure it and you see alpha squared at the time that it's 0, then like its state sort of changes to being like 100% amplitude on 0. And similarly, if you happen to see 1. So this is actually, this truly happens, and it sort of says that nature actually is probabilistic in some way. More generally, if you have 2 qubits and you measure them, you know, you see 0, 0 with probability alpha squared, 0, 1 with probability beta squared, etc. Again, it makes sense. These are non-negative numbers that add up to 1. And the state collapses. And similarly, if you have 3 qubits or n qubits. Okay, so in general, when you put together all this formalism, I've told you all the formalism pretty much. A big quantum circuit kind of looks like this. It looks like a reversible circuit, except there's also some Hadamard gates thrown in. You put in your real inputs on the wires. It's just non-superposition qubits. You put in some scratch bits. You measure all the results. So you get a probabilistic output. It's kind of like a randomized algorithm. And hopefully f of x is correct with high probability. Yep.
So when you're saying that the state collapses, you mean that the measurement actively modifies the state?
It kind of does, yeah. By measuring, if you have some particles and like you haven't measured them yet, they're in like a superposition with all these amplitudes. But then when like you experimentally measure them, And like it's still, I guess, in physics not exactly clear what that means, but somehow in practice, when you measure them, they kind of snap into like a deterministic state where you have like all the amplitude on one outcome. And so like all of these qubits, once you measure them, will, all the like photons, let's say, will be either horizontal or vertical. Yeah?
So if measuring it affects the output, is it then reversible?
No, so measurement is not reversible. And again, I don't know any physics, but I'm told that this is some kind of like, yeah, not fully unresolved question about what's going on there. Yeah. But in practice, this is how it works. So this was an example quantum circuit. And I just want to mention one funny thing. Let me imagine having another Hadamard gate here. You have the same situation. This is what the Hadamard gate is, but you can't just multiply it against this for the same reason as before. You have this type mismatch. You have to expand it just as if it were a probabilistic circuit, and then you can multiply it. And in this case, the final amplitudes will be these, half, 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 and negative a half. And you do squares sum up to 1. That's the final amplitudes for this circuit. Let me mention just one funny thing, which again is kind of weird about quantum mechanics. Imagine this was like the physical circuit, and at this point in time, Alice like puts the first photon in her pocket and flies away. Bob puts the second photon in his pocket and they fly away. And then Bob does the Hadamard laser on his photon. In some sense, nature actually still remembers that these two particles are in a joint state and like kind of updates their joint state in this rule, even though they're super far apart. And like, that also is a little crazy. It's called spooky action at a distance. You may ask whether it allows faster than light transmission of information, which is supposed to not happen in physics, and it doesn't. Like, it's hard to see why. I mean, you have to think about it, but it doesn't. So that's good. Like, this is how nature really works, and it's consistent with the laws of nature. So that's the end of the theory, and there's some strange but true aspects to this. So, if you have an n-qubit quantum circuit and you want to mathematically analyze it, it's very hard because you have to keep track of these length 2 to the n amplitude vectors. And in physical reality, this is a weird thing. It seems that nature actually does this. You know, with randomized computation, the vectors are actually just modeling your uncertainty about what's the true state of the particles. But like in quantum bits, the true state of the particles is this like length 2 to the n vector of amplitudes. And like somehow nature keeps track of this. And like the qubits are not secretly in some definitive state. They're really in this superposition of states. Like it's just like this. Experiments have confirmed it. Okay, so now a little bit, the last 2 minutes, I'll go a little bit over time. Why quantum computers? What would we gain? Well, first of all, I say, why not? Physics allows it, so like you can build these physical devices, so let's do it. When Feynman invented the idea, he had the following thought process. Suppose, and physicists really want to do this, you wanted to like simulate a quantum system, or like you had a quantum circuit and you wanted to know like what are the final amplitudes, or what probabilities would you observe this and that. It seems you need like exponential time to do this with like a normal computer. But Feynman was like, well, the particles themselves are doing it, right? So why don't we just call them the computer? And then they're like doing the computation that we care about. And it also turns out that there's a few other problems that can be solved efficiently with quantum circuits that we don't know how to solve with classical circuits efficiently. And this is where it got kind of truly amazing. So the most famous such example is Shor's algorithm, invented by Peter Shor in 1994. And he gave a quantum circuit of polynomial size for factoring, which is something we don't know how to do efficiently, classically. And thereby crack RSA and everything. And prior to 1994, like quantum computation was kind of like a funny concept. And then once he showed that it could factor, like people got really, really interested in it. And like a lot of money and thought has been put into actually building quantum computers. The other interesting algorithm is Grover's algorithm. Let me go through it for time, but it's the other famous algorithm. And the essence of it is on the current homework. So you can sort of get a sense of what quantum algorithms are like from this homework problem. So finally, you might say, all right, well, this sounds great. Now we can factor efficiently. So give me the quantum computers. Where are they? And at the same time, it's like asking, like, where are the flying cars? Like, come on. Like, it's consistent with the laws of physics that we should have flying cars. So how come we haven't got like flying cars? And it's the same situation. Like, people are working on it. It's like an engineering problem. Like, it's totally feasible, according to the laws of physics. It's just it's hard to actually build them. They did it on a small scale in 2012, and they factored the number 21. And like, this is like the real picture of the physical device. And it was like, it's 3 times 7 with high probability. Yeah, so let me end the story by taking you all the way back to the 1840s. Got all the way up to the 90s. We'll go back in time. There's this guy, Charles Babbage, and he's like, I have this awesome theoretical idea for like a universal computing device. It works great in theory. You're going to need a lot of punch cards, but that's my idea. Didn't exist, but there's this other person, Lovelace, and she was like, this is really cool. Even though the computers don't exist, I'm going to write some code to like compute the Bernoulli numbers or something on Babbage's like theoretical device. And she's like, as soon as this gets built, this is going to be really awesome. And then, like 100 years later, they did it. Like, hooray. They finally built computers, and they could run this code and stuff. So the moral of the story with quantum computers is, patience. Like, we don't have them yet. We're going to build them, it seems, because it's consistent with the laws of physics. In the meantime, we only know like 1 or 2 cool quantum algorithms, like the Shor factoring algorithm. So what we can do in the meantime is, program for quantum computers. So in the meantime, you should be a Lovelace and see what you can do with quantum computation. OK, see you at the exam tomorrow. And then have a good carnival.